We are recording. You can start whenever you're ready, Matt.
Oh, okay, gotcha. Good morning, everyone from Kotzebue, Alaska. The tropics of the Arctic this summer so far. It's been exceedingly warm here and dry as well. So it's shorts and sandals most of the summer. So I'm curious, maybe at the end I'm just curious to hear back from other folks around the northern latitudes if they're exceedingly warm as well. A bit concerning for some of our infrastructure up here with our reliance upon permafrost for foundations and whatnot. So we are quite concerned with the heat. So let's get started. So wind energy in the Arctic, Kotzebue Electric Association has been dabbling in wind power since the early 90s. We get pretty strong winds and consistent winds as well. Our wind resource is good in the sense that it's not too strong. We do get occasional peak winds of 70 miles an hour, but for the most part, our winds are higher winds are in the 20 to 35 mile an hour range, which is just right for wind production. So this image you're seeing here is kind of a winter scene of part of our wind site. This is during construction of our two large EWT turbines, which we'll talk a little bit more about. But that's the first one going up right in the middle by the Y in energy. And then the second one, the base section of the tower, is up under the sea in Arctic. So let's get rolling. Everything coming through okay on your guys' end?
I believe so, yes.
Okay, here we go. So, Kotzebue Electric Association, we're in the northwest part of the state, about 30 miles north of the Arctic Circle. We've got about 3,200 folks here. We have 11 villages surrounding us. We're the hub of those 11 villages. The smallest being about 110 people, the largest almost 1,000 people out in Selawik. We're served daily by jet service, passenger jet service on Alaska Airlines from Anchorage twice a day. Then we get several cargo aircraft coming up 2 or 3 times a day as well. So we're a busy place here in terms of air traffic for passengers and freight. You can see where we are on the ocean there. We're above the Bering Strait. Our first barge of the season just came in a couple days ago, brought in a bunch of new boats and cars and supplies, construction materials. So we get 2 barges a year. We get kind of an early barge in July, and then our last barge is in September. And those come out of, they originate in Seattle, and they stop in Anchorage and then drop off things along the way in Bethel, Nome, and other places along the way. So we have essentially a wind diesel hybrid power system here at Kotzebue Electric. Our average load is 2,500 kW. We peak out at 3,500 kW in the winter, usually in about January or February. We'll get our peak load. Our lowest loads are in the summer, so nighttime in about June or July, we can get down to close to 1,400 or 1,500 kW. We've got 6 diesel generator sets ranging from 725 kW up to our largest one, which is rated 3080 kW continuous. And at this point, we're importing about 1.2 million gallons of diesel fuel annually to provide electric power for the community. We used to be at about 1.45 million gallons annually until we installed our 2 larger wind turbines. So that's definitely reduced our import, and that's kind of our annual measure, is how much less are we bringing in to top off the tanks when the barges come. So we have 19 wind turbines total. 2 of those 19 are our large 900 kW EWT turbines, and the rest are smaller machines that we installed in the late 90s and early 2000s. So those are all smaller, less than 100 kW machines. Getting about 4 million kilowatt hours annually from our wind production, and that's anywhere from 15 to 20% based on how windy it is, how well the wind turbines are working, and just varies through the year. Our cost of electricity here is a little tricky. So we have a program in Alaska called PCE. So members of the co-op, we're an electric co-op, pay 39 cents a kilowatt hour if they're not getting PCE, which is basically any commercial businesses, federal facilities, essentially non-residential. Cost to members who are getting PCE, it's about 20 cents. There's a 19-cent credit coming from the state of Alaska for power cost equalization. And that's for residential members, but a key member of that group is the municipal facilities, which includes the water system, sewer system, street lighting, all that are PCE. So we've got quite a bit of turmoil going on in the state right now with PCE, and that possibly going away or being limited. So we're all watching the news pretty close here about PCE. So in the near term here, we may all be paying 39 cents per kilowatt hour or more. So a little more detail on our energy system. Like I said, we have 19 turbines, 17 are smaller ones, and 2 large EWT 900 kilowatt turbines. The EWTs are direct drive, AC, DC, AC, inverter-based turbines. Performed fairly well. They were installed in 2012. We've had a rash of trouble with one of the machines with the converter system. The turbine, as far as the blades, generator, everything is fine. It's the power conversion system that takes variable AC, converts it to DC, then back to AC grid power, has been giving us trouble. But otherwise, they're very nice machines, very reliable and easy to work on, all enclosed, and controllable as well, which is a very nice feature I'll talk about later. We also have a lithium-ion battery. It's a 1.25 megawatt inverter by ABB, and that's coupled to a 950 kilowatt hour lithium-ion battery, which is made by SAFT. So between the two, we have essentially a 1.25 megawatt genset, we call it. It's we kind of treat it like a small generator that we can start and stop immediately. And it's come in handy for essentially spinning reserve for us and kind of acting like a UPS. Diesel genset automation is a big part of our system. We have an automated system through our SCADA system. And part of that system is 2 engines that we use quite a bit with the wind. So we've got 6 engines total, but as we're using more and more wind, we're using smaller and smaller diesel engines. And the 2 that we've most recently added to our fleet of diesel engines are an EMD 8-cylinder 710 EFI, which is rated at 1440 kW. And then we also have a small Cat C27 that's rated at 725 kW. So between these 2, the EFI and the fast starting CAT were able to handle changes in the wind and changes in load pretty quickly. So between the battery and then these two small diesel engines, we can react pretty quickly to load and wind changes. Another component on our power system that we use pretty often when we have a lot of wind is a 450 kilowatt electric boiler at our local hospital. The hospital is our largest building here in Kotzebue. I think it's 90,000 square feet, large place, and it has a very large hydronic heating system. We were able to work with the hospital to essentially size and install a 450 kW boiler that would allow us to push excess wind power when we had it to them at a rate that saves them money. So they're purchasing this excess wind power at a cost equivalent to half the cost of their heating fuel cost. So this works out well for them, and it provides a little extra revenue for our cooperative. So when it's usually about over 25 to 30 miles an hour, depending on the season, we either need to pitch our blades to reduce wind power, or we can capture it and put it into heat. And with that, they're saving about 20 to 25% fuel savings per year at the hospital. So that's worked out very well for them, and it's gaining traction here in the community with other facilities that want to try to do that. So it's gaining popularity, and we think it's a good way to utilize renewables to help reduce the cost of energy, heating energy, electrical energy, and heating energy in the communities. Next page. So yes, this is a busy slide showing all sorts of stuff we got going on, and it's kind of meant to be that way because it is. There's a lot going on and a lot to keep it going. And in the lower right is the community. The whole drive of trying to use all these technologies is to reduce the cost of living in our community. The biggest cost being for electrical production is importing diesel fuel and what that price of diesel fuel is going to be every year. So right now, we're about to order our fuel, or it's about to be loaded on the barge to come up here. And luckily, there's sort of a drop in number 2 heating fuel prices. So it's looking to be about $2 a gallon. However, in past years, due to the price of world oil and whoever controls it, it spiked and spiked dramatically about the time we have to order our diesel fuel. And then we're stuck. The price may go down on the world market, but we're stuck with that price of diesel fuel for the whole year. So spikes in the price of diesel fuel have really motivated us to try to use various technologies to try to reduce that hit on our community and the cost of living for everyone. So we've got our wind turbines. We've got the excess wind to heat the hospital. We've tried to optimize efficiency for our diesel generators. We have a lithium-ion battery we're using for various things, including helping the diesel generators for peak shaving rather. And then one project we haven't quite gotten off the ground is the one on the middle right side, which is the GE Clean Cycle ORC generator. It's essentially a 140 kilowatt organic Rankine cycle generator that is going to utilize exhaust heat off of our diesel generators and then cooling from the atmosphere to drive this small turbine. We're hoping to possibly complete that this fall. We need a crane to set a new silencer and exhaust system on the generator, and then finish off the controls. So that's another technology that seems to be improving more and more as time goes on and getting simpler to install. So we're trying all these things in an effort to drive down our community cost of living. And I'll keep moving on here to the next screen. So this is a better shot of our large turbine, our EWT 900. These are on 75-meter towers, about the tallest tower you can get for it. And in the background, between the crane and the tower, those are our AOC 50 kW Atlantic Orient Corporation turbines. Those were installed in the late 90s, 1997, 1998. And much larger scale and much different technology. The smaller machines are induction generators with gearboxes. The larger machines is a direct drive, variable pitch blades, all enclosed tower, much more friendly to work on in the elements. So this is our bread and butter. We have two of these machines, and between the two, we can achieve power penetrations of 75% pretty consistently in the warmer months. We haven't attempted to go diesel off yet, but we don't have quite enough power to go diesel off, except maybe at night in the summer. But these have proven to be very effective machines for controlling power output and just generating a lot of wind power for us. And I put on there winter construction. We are surrounded by tundra, soft, pretty much wet tundra. And our cost of gravel road pad infrastructure is incredibly expensive here. Our gravel source, we don't have one. So all gravel material is barged in from about 20 miles away and handled several times. And the cost of gravel is just, it's a project killer. So what we've had to do with all our turbine construction projects is work in the winter on the frozen ground. So we have a pretty narrow window for doing this work and a fairly long logistics planning cycle. So these turbines and cranes had to be brought in the summer before, so August, wintered over, and then starting in about February, we get a little more daylight, start building roads, snow roads, and then mobilizing all the equipment to the site. And the foundation was done the summer before as well, or the spring before, so it's a challenging prospect to do it. It's doable. It's just a long, got to plan quite far in advance for doing these things. Just seeing if there's any questions.
Right now we have no questions.
Okay, we'll keep rolling here. This is a picture of our battery, which is located in our substation. So just sort of what's going on here is we have the poles with the cables and switches on top. This is our substation right behind our power plant, which is the brown building. And this is where we step up voltage from our generator bus voltage at 2400, 4160. We step up to 7212.5 kV. And the gray building up on the pilings is our substation switchgear. We've got 4 breakers in there, 15 kV breakers that go out to our 4 feeders feeding the town. On the end of one of those feeders, feeder 4, is where our wind turbine site is located. So a feeder that previously had been a lightly loaded feeder has become a highly loaded feeder, bringing power back from the wind turbines into the substation here. In the forefront of the substation building there is the SAFT lithium-ion battery container. We're sort of running out of space around our power plant, so this was the best spot we had for it. And you'll notice it's still on a trailer because we couldn't quite get a crane big enough to take it off yet. And it just works as a nice foundation. So you just got to make do with what you have. So it works just fine. The SAFT lithium-ion container is just filled with lithium-ion containers about the size of a desktop PC, all stacked into racks. On the left side of the container, there's kind of a beige box. That's the HVAC unit, and it provides cooling when it needs it. So it could be spring, summer, and fall, depending on heat load on the batteries. It does have a chiller built into it, but it's also tied to our heat recovery system in our powerhouse. So to heat it in the winter, we're using jacket water heat to provide heat for it. So out of this container with lithium-ion batteries is essentially 800 to 900 volts DC. And those go through a duct of just a whole bunch of copper cables. They connect directly to the inverter. The inverter is in the powerhouse, and we wanted to have the inverter inside because that's where a lot of the control work is done. Not so much is done in the battery itself, but in the inverter. So we wanted to have access to the inverter in the powerhouse. And I think that's the next picture. Oh, that's the wind engine. Okay. So this is our small 8-cylinder EMD 710. EMDs are 2-cycle diesel engines, very popular for locomotives, tugboats, and also power generation. It's very quick responding and also able to put out quite a bit more power than its nameplate. What we have done with this engine is base loaded it with the wind. So we're able to, with our system load of say 2,500 kW, capture wind to drive the diesel load down to about 800 kW or so, maybe even 700, all on this engine. However, if we do lose wind power, there's a problem. This engine can put out almost 2 megawatts of power pretty fast. And then with our battery also online, between the battery and our little wind engine, we're able to keep power on in the community. So it definitely puts some load on the engine and the battery, but we don't shut anybody off. Prior to having this engine and the battery, we would essentially run a negative reserve on some of our older engines. And if we did have a problem, we would go into a load shed mode because the engine couldn't maintain frequency or voltage. So we'd have to shed a feeder, which wasn't very popular with the community. We were having several partial power outages in the community per year due to wind power. So this has really done well for us in terms of fuel efficiency, but also keeping the lights on, which is what everybody wants. And then this is our electric boiler at the hospital here in Kotzebue. I'm not sure why it's orange. I'm not sure who took this question, but the boiler itself is gray. I'm not sure why it's orange. And the floor is not green either. But anyway, here's a picture of the boiler. The gray box with the touch screen in the middle and the 2 green lights is our remote control panel. So that control panel was installed by us, Kotzebue Electric, and we're tied to it via wireless link. Inside it is a small PLC that operates the heating elements. The heating elements are in the orange box on the left side. That's the actual electric boiler. So what we're doing is operating the elements based on how much load we can provide. So it's worked quite well. There's 450 kW of power there. We've achieved that pretty regularly, and also it achieved long run times where they're not operating their oil-fired boiler at all. So I think there's been some 24 to 36 hour periods where they've just been running on excess wind power to heat the hospital. So this, the electric boiler is plumbed into the return line to the oil-fired boilers. So this is essentially preheating the oil-fired boilers. So there's no controls interaction between the electric boiler and the oil-fired boilers. They're essentially, the oil-fired boiler controls just see hot glycol coming back to them so that they don't turn on. And also this, our controller will regulate the power output too, to not overheat the glycol system at the hospital also. So it'll regulate the temperature output to whatever they want. I think it's 180 degrees Fahrenheit. So this has been very effective for saving them heating fuel, and also providing us with another revenue stream to help support our turbines and utility co-op. So yeah, we've got a lot of things going here, but it's taken a lot of time to get to where we are. We've been at it 25 years, maybe even more. People have always said, it's so dang windy around here, why don't we use this wind for something good? You know, that was in the 70s, 80s. There were some attempts with some small Bergan turbines at the local community college. But yeah, in the late 90s, utility scale wind was becoming available, and Kotzebue Electric, the board of directors, and our retired general manager Brad Reeve said, let's try this. We've got this wind, we've got fluctuating oil prices. Let's see if we can utilize this wind to help save the community money. And there's been a lot of help along the way, though, too. The National Renewable Electric Cooperative Association, NRECA, funded the initial wind studies. A large funder of the initial wind project, which began in the late 90s, 2000s, was U.S. Department of Energy and NREL. And then for our two large turbines, the state of Alaska was a very significant contributor with the REF, which is the Renewable Energy Fund. That was a fund created due to the spike in oil prices in 2008. The state of Alaska is an oil state, and when the price of oil spiked to over $100 a barrel, the state was bringing in a lot of money. So they did create a fund at that time called the Renewable Energy Fund, and that afforded us the chance to procure 2 EWTs, our lithium-ion battery, and the boiler at the hospital. So that was a significant grant that we received to do that. Also along the way, we did upgrade our diesel plant, and that was a loan through the USDA Rural Utility Service. So we did get a loan. That was essentially to replace the switchgear in the plant and go to modern switchgear with a SCADA system. So it's all automated. And that was a significant project, but it afforded us the ability to automatically respond to changes in load, but also changes in wind power as well. So we can downshift as wind increases from large diesel engines to smaller ones automatically. And then there's been success along the way, but failures. You know, nothing's going to work right every time. Wind has been frustrating at times, but otherwise it's been great at times. So it's going to have to work with it. The good thing is wind technology, wind people, the talent pool of people working with wind is getting deeper around the world, and integration of wind knowledge is evolving as well. The other big component is energy storage has long been the holy grail, and it seems like it's here and it's working. So we are strong proponents of energy storage in terms of not just for renewable issue, but also in terms of providing flexibility to your diesel engine dispatch system. And you know, microgrids are the cool thing now, and I guess we're an islanded microgrid, so they seem to be getting a lot of attention now as far as technologies and interest. So things are really coming together that weren't there back 25 years ago. So it's encouraging to see that. So I kind of put this slide in because I wasn't sure who would be in the audience, but in terms of if you're interested in wind and how it could work for your area or community or country, wherever you're at, you know, why is it worth messing with wind power, and why do you want to mess with it? You know, and I'll sort of talk about from our perspective. Our biggest issue was the fluctuating annual expense of diesel fuel. We couldn't count on how much it would cost every year. So, like I said, right now we're in a lull as far as the cost, but situations in the Middle East or somewhere else could change that. And we don't have any control of that. So by importing as little fuel as we can and utilizing local fuel, that helps the economics of our community. The heat generation from excess wind power is another revenue stream for our cooperative, but it also reduces the cost of energy for whoever might be absorbing it. In our case, it's our local hospital. They're saving quite a bit of fuel and cost in terms of their cost to operate their facility. Workforce opportunities, you know, this is another way of creating jobs in the community. If you're bringing in less fuel every year, that's quite a bit of cost. However, wind turbines don't run themselves, they don't fix themselves, but it's an opportunity to create employment to help keep the wind going amongst other technologies in your power system. So it's a way to create workforce opportunities both in the construction, during the construction phase, but also the operational phase. You know, it's always good to help the environment. I put an air permit note on there. We've got a weird situation where our little wind engine we run with our wind has a limit on how long we can operate it every month. So even though we're providing 60% of the power for the community with wind, we have to shut off this wind engine because it has an air permit stipulation. So it's a unforeseen consequence of a air permit situation. Energy, go ahead.
We have one question.
Yes, go ahead.
With as many wind turbines as you have in Kotzebue and with the large bird population up there, has there been any problems?
No, in fact, that was a big concern, especially at the outset of the project in the 2000 or so. We did work with U.S. Fish and Wildlife Service to essentially, they did a walkthrough during the migratory season every spring for about 5 years. And they also do something around the community called like listening posts, where they actually send out some biologists and listen for birds, like for a whole day. They just go out there and sit there and listen. And they would actually do that near our wind site. And essentially what they found is there was no changes, we didn't have any bird kills, and there was no pattern they saw as far as the wind affecting bird migration or something like that. And I think we've got a letter from them, and that was through our local, we have a U.S. Fish and Wildlife office here in Kotzebue, so working with them. I do know that other projects have come into challenges with Fish and Wildlife Service and had to get into major studies, which is costly and time consuming. But we're able to not have that challenge as much, but other projects have experienced that. So hope that answers the question. So, okay. So energy security and resilience, that's kind of relates to the first bullet point there in terms of diesel displacement. If you're using wind to reduce your diesel import, you have a little more security there, if just in case a barge can't get in, something happens, you're not able to get fuel, you're less reliant on outside suppliers to provide your power. Community pride. It's kind of an interesting thing that as one village gets a wind turbine, the next village over says, well, we better keep up with the Joneses and get one as well. So that's becoming a interesting facet to the development of renewable energy. There's always a little friendly competition between communities. Nome and Kotzebue are two good examples where extremely rivalry on the basketball court, and we were also competitive in our wind turbines. We had 17 wind turbines. Nome installed 18, and then we put in 2 more, so now we have 19. So 1 more than Nome. So it's been an interesting development for renewables in that way in terms of community pride and having renewables. So it could be a combination of all the above, or maybe even something else for utilizing wind power in your community. So there are several technical issues with wind power in the Arctic. One of the big ones is heat. You know, many power systems in the Arctic recover heat from diesel generator sets. We do. That's how we heat several of our facilities. We also provide heat to the water system here in Kotzebue. So we have a city water, a treated water main that comes into our powerhouse that we're heating from 38 degrees to about 45 degrees. So it's low grade heat, but it's a pretty significant amount. And so utilizing wind reduces the amount of heat that's coming off your diesel engine jackets. So we're having to balance that in the wintertime as far as how much wind we can capture in order to keep things warm. So what we're looking at now, we have installed an oil-fired boiler that runs on used engine oil. We're looking at installing an electric boiler in the plant as well to try to keep things warm so that we can start engines as we need. Our other big problem here is our plant is kind of old and drafty. For 50 years, our plant was designed to get rid of as much heat as possible. 40 below out, it's still hot in the plant, and that's just fine. But as we're switching to smaller engines, certain parts of the plant that are not as well insulated or drafty are getting cold. So it's something to think about if you have an older power plant, trying to keep things warm for when the wind does stop. Diesel plant capabilities, that was one of our projects, was to automate our diesel plant so it can reliably start and stop engines automatically. Not just start and stop, but start, sync to the bus, load share, stop. Is your metering in good place? KW, kVAR, kilowatt hour, all that. And then modernizing your speed and voltage controls. Completely replacing a power plant probably isn't necessary, but at least having modernized switchgear and controls will go a long way. Even with an old engine, an old diesel engine, if you have modern switchgear, that'll go a long way towards automating that older engine. And then, local technical capabilities is a huge one. We haven't been totally successful yet in having as much capability as possible on our staff to fix everything. We can fix about 75% of everything, but we still bring in our EWT wind technicians twice a year. We actually have an ABB engineer here right now. But if you need to do that a lot, flying technicians in and experts, it's just gonna reduce the savings you're trying to achieve from wind or whatever renewable. So that's trying to build that capability on your staff is critically important. With the advent of the internet and fast internet in most places, we've had good success with remote technical support. So instead of somebody flying out from wherever, say SAFT or the battery company, they can come in through the internet and try to diagnose a problem or something like that. So, because you're going to have problems and mysteries with machinery, and bringing people in is always expensive. So yeah, this is a picture of our powerhouse. Got the exhaust stacks coming out the top. This is just after a blizzard we had. And the two, those are our radiators, kind of the middle left of the picture that don't have snow on them. That's one of our big challenges right now is our radiators are outside, which is great in the middle of summer right now because we're trying to get rid of heat as much as possible. But in the wintertime, with the fans off, the radiator fans off, the wind is blowing through the radiators, just robbing heat from the powerhouse and from the engines. So we're kind of looking at enclosing the whole radiator system and then controlling some louvers to help regulate that. But in the end, got to keep the power on and keep it reliable. So try to conserve heat as much as possible. A quick note here on wind resource and location. Like I said, our wind resource here is strong. It's not super strong. A good example might be the Aleutians, where they have really good winds. It's probably too good. They see 100+ mile-an-hour winds, not on a regular basis, but pretty often. So they've got a lot of wind. It's almost too much wind. So where we're at, it's a pretty a medium resource, but it's also not a violent wind as well. We've also got a pretty flat terrain here, just low rolling tundra hills. So it's a good situation here as far as our wind resource being pretty smooth and consistent. Tops of hills or mountains aren't always the best in terms of icing, and then variability of wind. Mountain tops can tend to have wind shifts or shears or whatever happens at the top of mountains. So you may have strong winds, but they may not be consistent winds that you'd see down in a lower area. Here in the U.S., we have the Federal Aviation Administration, who seems to extend their hand more and more in terms of away from airports, trying to protect aircraft, which is always good. But there are a pretty significant limitation on where you can install wind power. It's definitely good to consult with them very early on in your planning process, and plan on probably putting some obstruction lighting on a wind turbine. And that obstruction lighting system might be pretty expensive. It might be $5,000 for one obstruction light, depending on what type. So not cheap for sure. And then there's some reliability issues. So if your obstruction light goes off, you better deal with it. You got to let the FAA know, all sorts of things. And for us here, the power line extension and access road costs are significant. Other parts of the world, gravel and road costs might not be much. But that's if your wind site is 5 miles away and you need to build 5 miles of power line and road, that could add up really quick. Co-locating with wind turbines with other structures worked well for us. Our KOTZ AM radio tower was already in the vicinity and located on the end of a power line. And we essentially said, well, we need power, and this tall structure will be with other tall structures. So it worked out well to co-locate those in one area for aircraft, so that they know there's the radio tower, wind turbines, all in this area south of town. And then another thing to think about is leave space for expansion. We never thought we'd be expanding as far as we have, and now we're kind of looking to expand more. So planning your site, plan for triple the space or triple expansion at some point in the future, because it's just a good way to, it's a learning lesson from us. Plan for more space. And then this is kind of the boilerplate of wind stuff, wind levels, low, medium, or high. For many years, we were at that low level with our smaller turbines. And then with our 2 EWTs, we bumped into the medium level, where we're getting 60% to 90% peak power penetration. Where we're hoping to go is high penetration, with being able to shut off our diesels and provide beneficial electrification where we can, excess wind to heat. That's where we want to go, and save as much fuel as possible for power generation, but also heating fuel for our members. Just what we've learned as far as evaluating options for wind integration, especially in the Arctic, because of the heat requirements of communities. Homer has a nice option on there for an electric boiler or a heat recovery module on Homer. So Homer is a great way to evaluate wind and different ways to use that wind power for diesel fuel and heating fuel reduction. Some manufacturers are making low wind resource turbines, basically larger rotors and different blade styles for lower wind resources. Another thing to do is talk to people who are doing it. The Chinook Wind Group down in Southwest Alaska have a lot of experience with wind going diesel off, and also excess wind into homes using the Steffes heaters. Give me a call or an email anytime here at KEA. UVEC is a Unalakleet Valley Electric Cooperative in Unalakleet, Alaska. And then Colville Lake, Canada, they're doing some interesting projects with solar diesel. So talk to folks that are doing it and see what they say. The professional industry is getting more and more up on wind and wind integration. There's a lot more firms and folks out there that have done this before, and there's a lot more technical talent that's out there. Go ahead. Was there a question?
I do not have any questions at this time.
Excellent. And funding availability. Here in Alaska right now, we're going through some interesting times in terms of state government funding. Federal funding is not so much of a option anymore as it used to be. So, you know, at some point, the technology, reliability of wind and energy storage, it may be time to go seek loans, long-term loans for installation of this renewable energy, and get off grants. So I think, in my opinion, the wind is at that point, and also the energy storage. So it's becoming bankable, I guess is the term I've heard. So here's where we're trying to head in terms of our Arctic wind energy, renewable energy vision. So we're at about 20% right now, 15 to 20%. We want to get to 50% or more renewable penetration in terms of our importing fuel. That's kind of what we're seeing now as economically viable. And to get there, we're going to need more wind power. So we're looking to double our installed wind capacity. At this point, looking at similar direct drive turbines in the megawatt scale. Also adding solar power. We do have some funds right now to do solar, and we see that as a nice bump in predictable KW coming in during the middle of the day for about 3/4 of the year. So wind, adding solar, and then also optimizing our diesel plant automation and adding that auxiliary heating to keep things warm, so that as we go to diesel off and there's no jacket water available, we'll be able to provide auxiliary heat from whether oil-fired or electric sources. We need to add more energy storage as well. We need to add enough storage and inverters so we can run the whole town for a short period of time, 15 minutes, half an hour, in order to start diesel power back up. And then possibly looking at long-term storage for time shifting. The flow batteries still seem to come in as a viable technology for longer-term energy storage, over 12 hours or more. So that's something we're looking at as well for longer-term energy shifting. And then moving to essentially an electric economy, trying to use as much of this renewable electricity as possible through heating, mostly heating, but other possibilities are out there as well, including electric vehicles. And that's what we just got on the barge a few days ago, was a Nissan Leaf, and it's pretty dang fun. We've driven it a little bit around town, and we drove it out to the windmills yesterday, and it's we're gonna run it through the winter and on an experimental basis to see how it does. But it's another thing that will help, we think could be more cost effective for folks here in Kotzebue, because our price of gasoline is so high, it fluctuates as well. And we've only got about 12 miles of road here in town, and our maximum driving speed's about 20 miles an hour, 25 miles an hour. So we see it as a viable transportation source, but we'll see how it does through the winter. And I think that's my last slide.
All right, and I have no questions so far. Does anybody have any questions they'd like to ask? Do you know of an entry-level opportunities for recent grads, mechanical engineering UAF, to get involved in wind energy or renewable energy as a whole within Alaska?
Ooh, yes. Several. Yeah, so as far as mechanical engineers, that is what I am, and I work for an electric company. Most rural powerhouses are about half electrical, half mechanical. So I've kind of got the mechanical training, but I've gleaned enough electrical up here to know to be dangerous. So there's several places to start out. One is some of the engineering companies based in Anchorage are getting definitely more and more into the renewables and renewable integration. So there's several in Anchorage, and those are either engineering firms or something like that. The Alaska Native Tribal Health Consortium has a pretty large energy conservation department that is trying to utilize renewables for water sewer system energy savings. Water sewer systems are pretty costly efforts in rural Alaska. So there's a group there at Alaska Native Tribal Health Consortium working to utilize renewables to reduce that cost of water sewer. And then some of the larger utilities in rural Alaska may have opportunities. KEA may in the future, but I know there's Nome, there's Bethel, there's Nome, Kotzebue, Bethel. The larger hub communities are definitely looking for talent that can help capture more and more of the wind that's out there. So hope that was a couple resources anyway.
All right, we've got a couple. Please elaborate on funding assistance KEA has received for wind turbines, energy storage, and wind diesel. For example, what % of various individual project costs has been funded by grants?
Okay. I would say in general, probably 90% of our wind infrastructures come from grants. The biggest one being the State of Alaska Renewable Energy Fund. I believe that was, gosh, I want to say a $8 million grant. There was another fund, a resource in there, then we contribute about 10% of capital funds, our capital funds, to that project as well. So that was the 2 EWTs, the battery, lithium-ion battery, and the boiler. So likewise with our U.S. Department of Energy grants in the 90s and 2000s, that was probably 90% federal grant and some 10% coming from our local, say, capital funds or whatever you want to call it, our local dollars as well. So we've been pretty lucky and thankful to get as much funding as we have from state and federal resources to do that. And unfortunately, I think a lot of those grant resources are drying up pretty quick.
Do you have much restriction on the wind in Kotzebue?
Say that again, restrictions?
curtailment actually on wind and
Okay.
Kotzebue?
Yes, so we do some curtailment, and I kind of glossed over that, so I'm glad somebody asked. So what we do is utilize the wind power to get down to what we call our minimum diesel set point. So in that case, we would get down to our usual level is about 900 kilowatts of diesel power, and depending on the load, so 800 or 900 kW, and then the rest of the power would be coming from wind. As we drop below that minimum diesel set point, essentially the wind is coming up and we're pushing the diesel lower. What we used to do is start curtailing at that point. But what we're doing now is turning on more load. So we start switching on KW load at the hospital boiler. And so we're not curtailing, we're pushing excess wind into that electric boiler. However, once that boiler is fully loaded up and then we start driving the diesel lower again, then we'll start curtailing the wind at that point. So once the battery's full, the diesel's at its minimum, and then the hospital boiler can take all it can, then we'll curtail. So there is still some curtailment going on, but with the electric boiler, it's quite a bit less.
All right, I think that's all the questions we have so far.
Excellent.
So thank you, Matt. Thank you for sharing with us.
Yes, thanks everybody for listening in, and I'm devising an experiment for this Nissan Leaf through the winter, and I'll hope to put some sort of results out next summer, see how it did.
We look forward to them.
Yeah. All right, thanks everyone.
Thank you.